As many of you are well aware of, there are a variety of powerful energetic paradigm shifts that are taking place here on Earth at this moment in time. For example, we have Earth electrification. The Earth itself is becoming more electrically active and alive. The global electric circuit is strengthening. And this is a process that first goes back to the Industrial Revolution, but has been accelerating since then, and perhaps now with the advent of cellular and satellite technologies, it's going exponential. We also have what's happening with the sun and solar activity. We are in a grand solar maximum. There's been 300 years of increasing light energy on our planet, and on top of that, we are in solar cycle 25 maximum at this moment in time, a solar cycle that has been 50% stronger than originally predicted. We also have what's happening with our solar system. There are a variety of powerful planetary resonances that have been unfolding at this moment in time, really starting back in 2020 and accelerating in 2025, 2026. And we can look to see what's happening outside our solar system. In 2022, we had the most powerful ever gamma ray burst be received here on Earth, thought to be a 1 in 10,000 year event. This is a gamma ray burst that originated from over 2 billion light years away, and it was more than 10 times stronger than any other gamma ray burst we have ever observed here on Earth. So this was a tremendously powerful influx of the most highly vibrational energy. Now, all these energies are working with the Earth. Earth electrification is happening more from an internal perspective. Solar activity, planetary resonances, and things like gamma ray bursts, they work with the Earth more externally, but all of them work with the Earth. And Earth's magnetic field is the great mediator, the connecting agent to all of these. Because Earth's magnetic field guides the flow of energy across the planet. It's generated deep within the core, at the very center of the Earth, but extends all the way out into space until it meets up with the solar wind. And Earth's magnetic field also guides the flow of these cosmic particles that come in from, for example, far distant celestial objects, the center of the Milky Way and beyond. And so if you really want to understand what's happening with these energetic paradigm shifts and what may be to come, you really need to have a deep understanding on Earth's magnetic field. That's why I'm really excited today to announce the release of my Earth's Magnetic Field Master Guide for everyone on the channel for free. This is a 2-hour deep dive into Earth's magnetic field, starting with the basics, but then we examine what's happening with the core, how the magnetic field moves through the mantle, and how it attenuates in the mantle before reaching the surface. We talk about Earth's magnetic field strength now and across time, how that changes with things like a geomagnetic storm. We talk about Earth's magnetic field more in the plasmasphere and out at the magnetosphere, the boundary of the solar wind. We also discuss the history of Earth's magnetic field, past geomagnetic excursions and reversals, and the current movement of the magnetic poles at this moment in time. And so by learning more about Earth's magnetic field, you will better understand all these other factors that are at play. And I think that's really, really important. And by learning more about Earth's magnetic field, you're also learning more about ourselves, because the universe in general is fractal in nature, and we are fractal to the Earth itself. We are the Earth. We have our own magnetic field, our own biofield. And so this is one way to better understand our own energy rhythms and flows as well. And so I'm really excited to present to you the Earth's Magnetic Field Master Guide, a 2-hour lecture that goes deep. I highly recommend you take notes, watch this multiple times, and with that, let's jump right in. Earth's magnetic field is a massive force field that shields the lower atmosphere and surface from high-power radiation from the sun and cosmos. Without it, life as we know it on Earth would be dramatically different, or perhaps not even possible. But what even is Earth's magnetic field? How is it generated, and how does it change over time? Why is the magnetic North Pole moving so quickly right now? Are we at the beginning of a magnetic pole excursion, or even reversal? These are questions we'll ask and best answer in this Earth's Magnetic Field Master Guide video. Today we're going to journey to the center of the Earth, the core, and then traverse all the way back and beyond to the edges of outer space, so we may learn about and better understand Earth's magnetic field. We'll discuss magnetic field basics and the different variations that exist in Earth's magnetic field over time, from pulsations to reversals, and we'll also discuss our very real human impact on Earth's magnetic field, which may be of surprise to you. This is a no shortcuts taken, sensational free deep dive into this topic. All the chapters are in the video description, so watch the video in chunks if you need to. By the end of this video, not only will you understand the geophysics of our planet much better, you'll also better understand the impact space weather, like solar flares, has on our magnetosphere and plasmasphere. Okay, let's begin. This is Geophysics Explained. To begin, let's zoom out and look at the larger system at play really quickly, which is the Sun, interplanetary space, and the Earth. Now, the Sun emits a bunch of light energy and charged particles. These are plasma ions. They carry a charge, and any moving charge creates a magnetic field. So, the solar wind, as it goes from the Sun out into interplanetary space, creates an interplanetary magnetic field. And it's this magnetic field that connects the Sun and the Earth together. Because as you can see here in purple, the Earth has a magnetic field, and it's where the interplanetary magnetic field and Earth's magnetic field combine that allows for a movement of energy from the Sun into the Earth plasmasphere system. This affects Earth's magnetic field. Earth's magnetic field is generated deep within the core. We're going to dive into that in depth soon, and you can see these field lines coming out, but you can also see that these solar wind field lines also go to the polar cusp. Now, within Earth's magnetic field, we also have radiation belts, ion belts, the Van Allen belts is what they're called, and we have the ring current, and then we have plasma sheets and flux tubes within the magnetotail, and then you have plasma waves at the magnetopause, which is where the solar wind interacts with Earth's magnetic field. So there's a lot that's happening to Earth's magnetic field from things like the Sun and other influences, even like Jupiter and Jovian electrons and ions. And this all impacts the magnetic field of the Earth in the human time scale, because any moving ion creates a magnetic field, and these can sometimes strengthen Earth's magnetic field or weaken Earth's magnetic field on time scales that we see, like during a geomagnetic storm. To put into context all the information that we're going to cover in this master guide, let's first examine how geomagnetic activity varies across time and how the rhythms, cycles, and waves of all frequencies are superimposed upon each other. And this inherently makes it difficult to understand what happened in the past in regards to Earth's magnetic field, and also to forecast what may happen in the future. But we have identified many of these different patterns and rhythms that exist within Earth's magnetic field. The highest frequency of those are pulsations. They can last just for seconds, up to a few minutes long. They can last for longer than that. Like pulsations can occur regularly, but their frequency can be just seconds to minutes. Then you have substorms and geomagnetic storms that can last just for 60 minutes to a few hours to even a couple days. And these are pretty powerful changes to Earth's magnetic field, but there is the storm, and then the storm finishes and Earth's magnetic field is back to normal afterwards. Then you have things like diurnal variations. Earth's magnetic field changes every 24 hours due to its rotation into the Sun, depending on your location on the planet. So these are regular changes that happen to Earth's magnetic field strength and size and shape due to that factor. And then you have things like geomagnetic jerks, which over the past 20 years have been occurring every 4 years. And these aren't that strong. They're only about 5 to 15 nanotesla in strength, but they do occur, and they are a lower frequency rhythm that we've noticed in Earth's magnetic field. Then at an even rarer occurrence, we have geomagnetic excursions, which seem to occur on the 10,000 year time scale. Sometimes more frequently, sometimes less frequently. The geomagnetic record starts to get hazy and fuzzy the further back you go. And then very rarely we have geomagnetic reversals, and these happen on the 100,000 year to million year time scale typically. So all these are combined on top of each other. You have pulsations happening during storms, which are happening during the normal diurnal variations, and maybe it's at the maximum change for a geomagnetic jerk at that time, and perhaps that's cycled within an excursion that's occurring. So it's hard to tease apart these things, but you can look at them individually to better understand what's happening to the magnetic field. Now, to better understand this, we can look at this graphic I made here, which is effectively showing in brown like the noise and the uncertainty of the geomagnetic record, the paleomagnetic record. The further back in time you go, the less certain data becomes due to a variety of factors. This can be age dating, uncertainties. This can be uncertainties in regards to the actual observations you're collecting. There's just more and more error the further back you go. So in general, you'll have better resolution and understanding of changes to Earth's magnetic field, of course, in the present, and then also just in the recent past. So just 1,000 years ago, we understand Earth's magnetic field pretty well based on a variety of things like intensity measurements from pottery. And then what is notable is the Laschamp excursion, which occurred about 41,000 years ago, is very well defined. And that is the most well-defined geomagnetic excursion that we have studied so far. And that is 41,000 years ago. So if there was a geomagnetic excursion that occurred before that, which was equivalent or stronger in strength, then that would have shown up even more readily in the record, but that's not the case. Now, there are excursions that occurred before Laschamp and after Laschamp, but they are more uncertain in their dating, in their time window, and in their strength, and where the magnetic pole was drifting and everything, because the signal was not as strong. So it's a signal to noise ratio. And we have here in green things that are very uncertain, and then things in gray which are more certain. And another thing that was very certain, that's very easily observed in the record, the paleomagnetic data, is the Burns Matumaya reversal that occurred about 780,000 years ago. So that was the last geomagnetic reversal that we had, and we are now living within that geomagnetic field arrangement. So again, the closer we are to the present, the easier it is to understand these things and to track these changes. And the further back in time we go, the more difficult it is. So the fact that the Laschamp excursion is so strong is a good indication that that is probably the most significant geomagnetic volatility we've had over the past 50,000 years. Now, there is nomenclature that we have for these polarity intervals and excursions. You can look at them here. Mega chronozones and super chronozones, and this is just the jargon of paleomagnetism, but this just highlights the fact that there are different frequency rhythms that exist within Earth's magnetic field, most of them on geologic time. Now, the Laschamp excursion did happen during the Neanderthals, but we're not Neanderthals. All these variations combine together across time into a chaotic order/pattern that is hard to predict. So that is important to understand at the outset of this, because as we go further back in time, things are going to be less certain. We have to rely more and more on less data points and more models and statistical analysis, which inherently adds noise and degrades the quality of actual interpretation that we can come to. Now let's travel to the core. Let's look at Earth's interior, the mantle and the outer core and the inner core, and talk about some of the different observations that we know and some of the different theories that exist as for what is actually happening at the core of the planet and what is creating this magnetic field that is protecting us on this planet, because we really don't know at the end of the day. There are different models and theories, and some are more scientifically accepted by the mainstream than others. But until you've actually gone to the core, you don't know what's happening there. You can take magnetic field measurements from space at lower frequencies that help you to pierce deeper into the planet to make direct observations of the magnetic field. But we really don't know what we don't know. So there are a few different things that we're going to cover here. The nuclear fission georeactor is a little bit of a controversial but sensible theory as to what's happening in the inner core, and it potentially is also what contributes to the generation of the magnetic field. But let's start with the right here. This is very well known. This is seismic waves that have traveled through the Earth. You can see here the surface and then the upper mantle, the transitional zone, lower mantle, outer core, inner core. and this is all lined up with this. And you have sound waves that can travel through materials, and you have compressional waves, these are P waves, and then you have S waves, which are shear waves. So they travel slightly differently. One of them is compressing particles together, and the other one is shearing them against each other and propagating that way. What we see is that the compressional P wave and the S wave increase in velocity as the density of the mantle increases. But then the P wave velocity drops and then starts to go up again as it goes through this zone here, the outer core. But S waves, shear waves, which cannot travel through liquids, drops to near zero before returning back again. And we get this signature that is less than it was in the mantle, but still more than zero for this zone here, which we've labeled the inner core. So the fact that shear waves, when propagating through the earth, and this is sound waves and energy that's created from very powerful earthquakes that have given us this data, show that there is a zone within the earth that is liquid. It has liquid properties. So it is the outer core. By density measurements and gravitational measurements, we've determined that it is mostly an iron-nickel alloy, and it has liquid properties, and that the inner core is a solid iron alloy. The most well-accepted theory for how Earth's magnetic field is generated is that there is a geodynamo that exists within the outer core that generates this magnetic field, and that magnetic field then propagates through the mantle before reaching the surface and out into space. We're going to talk about that more in depth on the next slide, but I want to now go into the nuclear fission georeactor idea, which I think is very, very sensible. So the idea is that gravity pulls the heaviest elements, such as uranium, to the center of the core, concentrating them sufficiently for a natural georeactor to occur. And they've actually have found natural georeactors, so it's not at all impossible for these to occur on a much larger scale within the center of the inner core. Now, because a georeactor, it's splitting uranium and fissionable material apart, it produces light elements in the process, notably helium. And so these light elements, they have a very low density compared to like uranium. They would want to move away from the inner core. So they would escape to a subshell. And theoretically, the movement of these light elements, because they would be ionized, they would carry charges with them, they would create currents and everything due to various things taking place like Coriolis forces, they would generate a magnetic field through their churning, similar to the geodynamo theory of the outer core. And it is the start and the stop of the georeactor or georeactor pockets that could explain why the magnetic field undergoes excursions or complete reversals. So this makes a lot of sense to me, just based on the fact that gravity would pull elements such as uranium to the very, very center. And also geoscientists are still kind of grappling with why the Earth hasn't been cooling as much as you would expect from the initial models that were created. So there's clearly something that's keeping the Earth hot and alive and the core going, and it seems to be a stable process. There hasn't seemed to be a decrease in the energy being produced at the core. So if we look specifically here, we see that there's a subcore, and then there's this decay product and fission product subshell here, and then the nickel silicide inner core is there. And this idea of a nuclear fission georeactor and then that light element subshell, that is very, very plausible. And that light element subshell and the movement of it could be creating a magnetic field, either in contribution to a geodynamo within the outer core, or perhaps it is even stronger. But let's look more at the outer core geodynamo, because there's a lot of evidence that supports that this exists. Gravitational forces from outside planetary bodies like the moon, in addition to heat flow dynamics and rotational forces, would generate fluid convective currents within the liquid outer core, and this could generate a strong magnetic field. So that georeactor deep within Earth's inner core could also be what supplies energy to this geodynamo and helps these fluid convective currents to form, and they probably work together synergistically. I expect in the future that people will look at the outer core geodynamo and the nuclear georeactor as a one combined theory. So here we have the mantle in yellow, then we have the outer core in orange and the inner core in red, and we see these convective currents there, and we see the magnetic field lines kind of becoming turbulent within these currents, but then they flow out nicely. And this is the Coriolis effect that is causing this to happen, in addition to other physical forces. We can look here to see a artist's rendition, a model of what this looks like. There's your inner core there. You see these magnetic field lines in white streaming out from the outer core. This is the core mantle boundary. They look at the core mantle boundary and they model it and they map it to understand a lot of the deep processes that are happening on our planet, like geomagnetic jerks. And there's a lot of science that needs to be done there because this is still a very new field, and our understanding of this is based a lot on statistics and modeling and less on like high quality observations, though we're starting to get more of those as we put up more satellites that have high quality magnetometers into space. And then you see how the magnetic field propagates through the mantle, then out to the surface and beyond. The outer core geodynamo is highly likely, just based on the actual physical properties of the outer core that we know of through gravitational measurements, through seismic measurements, and just some of the physics that's well known. It is a geodynamo that is likely powering the magnetic fields of other planets as well, like Mercury and Jupiter and Saturn, Uranus, Neptune. They all have magnetic fields, and the geodynamo theory also is fairly simple and explains and can model their magnetic fields pretty closely in line with the measurements that we've taken of them. Once again, you'll notice the field lines are streaming into the core at the North Pole, and then they're streaming out of the core and the mantle at the South Pole. So this would represent the North magnetic pole, and the energy is going in, and then at the South magnetic pole, the energy is exiting this geodynamo system. So we're almost certain that Earth's magnetic field is generated within the core, whether this is the outer core plus the inner core or just the outer core through the geodynamo. But what is clear is that magnetic fields at Earth's surface are just a fraction of the field strength deeper inside the Earth and in the core. So at the surface, Earth's magnetic field strength is about 25,000 to 65,000 nanotesla. This is 0.25 to 0.65 Gauss. And 99+% of the magnetic force that's generated by the Earth internally at the core is absorbed into the mantle and into the crust, and this is known as tidal dissipation. So the field of magnetohydrodynamics sprung up to model and better understand this effect, and you can see these magnetic field lines here undergoing these waves and these oscillations within the mantle, very similar to hydrodynamic waves and things of that nature. Now, what we have recently learned is that the uppermost mantle is unambiguously magnetized. And this is a relatively recent development in geologic understanding, so you won't learn about this if you read papers from the 60s and the 70s. But what's been shown is that pure magnetite is pretty common in the uppermost mantle, which is that first 150 kilometers, and particularly in subduction zones and cratons, because cool and cold subducted slabs can carry these magnetic blocks down below the crust and even down to depths of about 600 kilometers. And magnetite is one of the most magnetic crystals in existence, and as a result, it has a strong ability to affect the magnetic field. So you have the mantle absorbing a lot of the magnetic field strength to begin with, and then that magnetic field is further attenuated when it reaches these magnetite zones that exist in the uppermost mantle and in the crust. And it may be those slabs that are changing the magnetic field expression at the surface. I'm going to talk about that more later with the magnetic North Pole and its movement and some of the strange things that we see in the Northern Hemisphere. We don't really fully understand what's happening below the surface of our planet. The crust is also magnetized. That affects the magnetic field as expressed at the surface due to things like igneous rocks and volcanic flows containing magnetite. But in general, what creates the magnetic field, whether it's a georeactor or a geodynamo or a combination of both or even other factors that we don't know of yet, that is really a big unknown. How much energy the mantle is absorbing is another big unknown. They have come to some measurements that show that Earth's magnetic field is like 2.5 millitesla in strength, but it was done through modeling and statistics. And it's one of these things of like, we discovered how far away the sun was, and then we revised that number over and over and over like the course of 50 to 100 years. How strong Earth's magnetic field actually is at the core, big unknown, but what we do know is that at the surface, it has a strength of about 25,000 to 65,000 nanotesla. And while that is quite a bit weaker than just a standard bar like fridge magnet, of course a fridge magnet won't have its magnetic field stretch across the entire planet, it is sufficient to protect our planet from high energy solar wind and solar flares and cosmic rays and things that can break cellular bonds and DNA and things that can kill us. So it's very valuable to have a magnetic field, and there is a lot that's happening within the Earth that's changing the magnetic field over time. It's really what's happening internally that is what's governing things like geomagnetic jerks and excursions and reversals. Now let's look at Earth's magnetic field, starting with the basics. Earth's magnetic field resembles the magnetic field from a large dipole bar magnet placed near its center. Now, a dipole bar magnet is one that has a clear south pole and a clear north pole, as colored here in blue and in red. And so 93% of Earth's magnetic field can be described as this dipole magnet placed at the center of the Earth and tilted 10 degrees relative to the rotational axis of the planet. This is what the magnetic field looks like. There are force field lines that emanate from the South Pole and then go and terminate into the North Pole. You can notice the direction of the magnetic force. Energy flows into the North Pole. So when you have something like a solar flare impact, usually you'll get aurora borealis at the North Pole because the energy is flowing that direction. It takes a stronger solar flare impact or a stronger geomagnetic storm to get aurora australis, which is southern lights at the South Pole, because typically this energy wants to flow to the North Pole. It's called the North Pole, but it's actually the South Pole if we're looking at a dipole magnet. Now, Earth's field is more complex than just this single dipole magnet placed near the center. It has numerous higher order poles, and there's also large scale anomalous features that exist within the Earth. So again, we can look here, and this is just representative. You see there's another dipole there and another dipole there, and they're offset and tilted in relation to the main dipole. And there are also non-dipole features. So again, dipole is just two poles. Di for two and then pole. The size, shape, and strength of Earth's magnetic field changes across space and all the different timescales, from seconds to eons. This makes sense because the magnetic field is quote unquote alive. There's a lot of things that influence it, from different waves within the outer core and also changes in the mantle to, like I mentioned briefly earlier, space weather impacts, crunching on the magnetic field and changing it, and plasma flows. All these things are changing the magnetic field. In general, it's pretty stable, both in its strength and its distribution of field intensity across the Earth and into space, but it does change. And an example of a change on the second time scale would be like a pulsation, which we'll talk about. An example of a change on the eon time scale would be like a magnetic field reversal. Now, something also to know that's important is that Earth's magnetic field, colored here in blue, is under the influence of solar wind and things like solar flares, which is plasma emitted from the sun, which is colored here in yellow, and that stretches the magnetic field away from the direction of these solar influences. So you have the magnetic field of the Earth that is crunched right here. That is the magnetopause. And then the magnetotail stretches far out beyond the Earth, and it actually passes further out than the orbit of the moon. So when you have a new moon, it passes into the magnetotail, and that changes the plasma dynamics within the magnetotail, which creates various energetic influences on the planet and also in near-Earth space. So Earth's magnetic field has some basic characteristics. It can, for the most part, be thought of as just a simple dipole magnet placed near the center of the Earth, but it is more complex than that. But in general, it is a field of magnetic force that surrounds our planet. Electromagnetism is one of the fundamental forces of the universe, and this is a force that has an electric field and a magnetic field. And so this magnetic field is a potential energy, just like gravity. The electric field is a potential energy, just like gravity. So when the potentials are changing in the magnetic field, then you're going to get changes in the magnetic field strength across space and time. What geologic studies have shown is that Earth's average magnetic field structure has been similar on the 10,000 year, 100,000 year, and million year timescale. So it hasn't really changed that much. Now, sometimes extreme magnetic field variations do occur, like excursions and reversals, which we'll cover closer to the end of this video. And it is notable that over the past 170 years, the magnetic field strength has decayed by about 10%. But as we'll see, this is still within the range of normal if we look at the historical record. So it's important to note that there are human timescale variations, and then there are geologic timescale variations in regards to Earth's magnetic field that are important to understand. And you don't want to get the two confused. After our journey to the core and the mantle, we're back at the surface, and now we're going to examine the magnetic field strength for the present day and for the past 12,000 years or so. So some of the headlines sometimes that you see are things like this, which is Earth's magnetic field is 35% weaker. And it's like an implication that it's 35% weaker compared to last week or last year. And these sensational headlines are common, but they're not grounded and they're not factually correct. And the reason why is because thousands of magnetic observatories exist around the world that collect data on Earth's magnetic field and, most importantly, the total field strength. So if Earth's magnetic field was quote unquote 35% weaker, we would measure that. It would be very clear because 35% is a big drop. So, for example, there is a magnetic observatory here just north of Edinburgh in Scotland. ESK is the abbreviation for it. And you can look up the magnetic field data for that location using a website like intermagnet.org. And we can look at the data here just recently on the 20th of October to the 24th. And we see that the magnetic field strength is starting there at 49,940 nanotesla, and it goes through variations due to storms, and here are the diurnal variations that you can see very nicely. And we see that the bottom of this scale is 49,885 nanotesla, and the top is about 50,000. This line is right at the 50,000 nanotesla field strength, and this is the magnetic field strength 2020 map that was created. So there will be an update in 2025. They'll release a new one, but we can see that in 2020, they observed this 50,000 nanotesla magnetic field strength at that location. And now in 2023, we're seeing that it's still just about 50,000 nanotesla. Things like geomagnetic storms can temporarily increase or decrease Earth's field strength, and sometimes very significantly, especially if near the poles, it can increase or decrease the strength by up to like 500 to 1,000 nanotesla. That's a very strong variation. Typically, it's more like 100 nanotesla. But that only occurs in certain locations, and these significant changes in field strength do not occur all the time, every single day, and it really depends on what type of space weather or solar flare is occurring. And these changes do occur over geologic timescales, but on the human timescale, you're not going to see Earth's magnetic field being 35% weaker in the span of a couple weeks or a couple months or even a couple years. So I wanted to clear that up. If you doubt this, I mean, a lot of these observatories are independently run. You can just find the location of the observatory that you want, and you can measure the magnetic field strength yourself for any time range. This goes quite a ways back, and you can use intermagnet.org to do that. Now, this is a nice little graphic here showing Earth's magnetic field and also shows the radiation belts. These are the zones of plasma ions that encircle the Earth, and it changes to the radiation belts that do have a pretty big impact on Earth's magnetic field during things like geomagnetic storms. So we'll talk about that a little bit more. You'll notice that these belts are contained within the magnetic field. So the magnetosphere holds these plasma ions close to the Earth, and it's actually a very efficient particle accelerator. So some interesting dynamics at play between plasma ions and solar wind ions in the magnetic field, and how it creates this environment to accelerate ions to relativistic speeds, which are speeds near the speed of light, and how, because these ions are moving, they're creating these magnetic fields of their own, and that changes Earth's magnetic field strength. So you can get a very large geomagnetic storm coming through that can depress and weaken the magnetic field, especially in the northern hemisphere. And that can create aurora down to latitudes that are quote unquote atypical, but it's not because the magnetic field strength is actually permanently 35% weaker. Again, you can look this data up yourself. So on that note, let's look at how Earth's magnetic field has evolved from 1840 to 1990. This is a map that's created from some of the historical data that was collected, and we'll see some changes here. We're going to look at the magnetic field intensity, the total, then we'll look at the horizontal and the vertical as well. So we're starting in 1840 when the first measurements took place, and let's specifically look here over Canada and then also over Siberia. These are the field lines. So 60 is for 60,000 nanotesla. This is at the 55,000 nanotesla right there. And it may be stronger there, but it's every 5,000 nanotesla that we get a new line. So let's click start. This is 1840. What you'll notice over the course of this 150 years, and we're seeing it already, is that this flux tube, this patch of higher magnetic field strength, decreases as the Siberian one increases. So this is one of the main reasons the North Magnetic Pole has been moving, is because this patch of magnetic field intensity has shifted from Canada to Siberia. Another thing that we'll notice here with this horizontal intensity map is we'll see how the South Atlantic anomaly, which is a zone of low magnetic field strength, has become even weaker just in the past 150 years. We see this zone right there pop up, and it's drifting closer and closer towards Brazil. And here we have the vertical component, and again we'll see this change from the Canada patch of magnetic field strength move over to Siberia. And there it is, it pops up, goes down a little bit, but then it'll resume and pop up again in just a couple of years. So there we go. And that's what's been happening, really accelerating over the past 30 years or so. So this goes to 1990, but really from 1990 to 2020 and to the present day, this has been accelerating even more. But this trend did begin back when we first started to get these measurements, even perhaps before that, almost certainly. We see these changes in the flux lobe there, moving from Canada to Siberia. And we're going to talk about that more specifically with a later slide. Now let's zoom back in time even more and look at the past 12,000 years and how Earth's magnetic field strength has changed during 4 different time intervals. We can look at 500 to 1,000 years ago, 2,000 to 2,500 years ago, 6,000 to 7,000 years ago, and 11,000 to 12,000 years ago. And these are a little difficult to understand at first, but I'll make it simple for you. This is the field strength there. B is a unit that represents field strength. This is showing it in microtesla. So 20 microtesla would be 20,000 nanotesla. 60 would be 60,000 nanotesla, so on and so forth. So we have that, and then we have our latitude there at the bottom. So this is negative 90 going to 90. So this would be the South Pole, and this would be the North Pole. And if we look at 500 to 1,000 years ago, we see two different lines here. We have a red line and a green line. And the green line is the model optimal fit for the axial dipole only. And the red line is the model optimal fit by combining the axial dipole and the axial quadrupole. So without really going specifically what that means, basically just look at the zone that they create and look at the strength that it has. Now the north magnetic pole right now has a field strength of about 60 to 65,000 nanotesla, and 500 to 1,000 years ago, we see that that strength is about the same. It depends on which model you look at, but here's the 60,000 nanotesla line, and they are both pretty close to that. Now, most notably, if we go here to 2,000 to 2,500 years ago, we see that there's a great fit between the red and the green line. So we can look at this really as just a single line. And we see here that at 60 for latitude, we see that the field strength was nearly 80,000 nanotesla. So about 76,000 nanotesla right there. And then it was down just a little bit under 60,000 nanotesla for the negative latitudes. So that does show a big strengthening there. You can see how the field strength has dropped from 2,000 to 2,500 years ago to just 500 to 1,000 years ago, and this is similar to today. But it's not a 2x decrease, or else the field strength would have been like 100,000 nanotesla or more. And it's not this data, and our current data is not outside what's normal, because we see here at like 6,000 to 7,000 years ago, we see that the field strength was even less than it is now. So there are normal variations that occur. 11,000 to 12,000 years ago, we see the strength was also diminished compared to now. And in general, this is, even though there's not really strong evidence of a geomagnetic excursion happening in the past 12,000 years, we do still see variations in Earth's magnetic field strength across this time period. And it shows that these variations can be fairly large if we were to think of them on like the human time scale, like a 5,000 nanotesla drop over the course of 50 years would be very alarming. But this occurs over hundreds, if not thousands of years. And the magnetic field strength goes up and it goes down depending on your location on the planet. So this isn't outside what is normal. This is just the last 12,000 years where we have a very high resolution on this data. The further back up you go, the fuzzier it gets, of course. So it's really just the past 12,000 years that gives us the best glimpse into understanding how the magnetic field evolves over time on this time scale. One of the things that can significantly change Earth's magnetic field, its strength, its shape, and its size on the human time scale is Earth's plasmasphere. We have within Earth's magnetosphere distinct populations of plasma ions. These are highly charged ions, so charged that protons and electrons can split apart, and because they carry a charge, when they move, they create a magnetic field. So there are three very distinct and well-studied populations of plasma within Earth's magnetic field, and these are the radiation belts. We see them right here. This is the ring currents, which we see right here. Then also the plasma sheet flux tube that exists within the magnetotail. And all of these interact together, and they also have their own variations that occur over time. So for example, with the magnetotail plasma flux tube, when the moon passes through that, it can actually cause that plasma flux tube to get pinched and to break off, and then for a reconnection event to occur, and that energy can stream towards the planet like we see here and start to go into the radiation belts and the ring current, and that can then change the magnetic field on a pretty short time scale. So for example, a geomagnetic storm can last a couple hours. That's like a substorm, for example, or it can last a couple days, but that's a pretty quick change to Earth's magnetic field. It's not a 20-year change or a 200 or 2,000 or 2 million year change. So the reason why ions like protons and electrons can change Earth's magnetic field is because when they move, they cause a force disturbance in the magnetic field. The magnetic field exists everywhere. The sun has a magnetic field, the earth has a magnetic field, it exists in interplanetary space as we talked about. And it's Ørsted's law that basically states that an electric field creates a magnetic field around it. So when there's an electric current, when there's a moving charge, this generates a magnetic field because it's disturbing these force fields. Most notably, it's the flow of Earth's ring current during a geomagnetic storm that reduces the strength of Earth's magnetic field, especially at the equatorial region. So here we have our ring current. You'll see there's an outer proton ring current, an inner proton ring current, and then an electron ring current that flows in a different direction. And the outer proton ring current actually splits into two due to solar pressure. And so these flow around the Earth at the equatorial zone, and the flow of these ions depresses the horizontal field strength. So that's one reason why you have a magnetic field strength of 50,000 or 60,000 nanotesla at the north and the south poles, but it's only about 25 to 35,000 nanotesla if you are in the equatorial regions. It's because of these ring currents. Now, these ring currents exist in the same part of space as the radiation belts, but you can see the radiation belts encompass a kind of a wider zone, whereas the ring current really is in this equatorial plane. And a geomagnetic storm, for example, can take radiation belts that are highly charged, like we see here, and it can deplete them very quickly and push the energy from the radiation belts down into Earth's ionosphere and into the lower atmosphere. And that also changes the magnetic field because the flow of ions will create magnetic fields, and some of them will add to the strength of Earth's magnetic field and others will detract from the strength of Earth's magnetic field. So you get big magnetic field changes on the scale of 10 to 50 to 100 to 1,000 nanotesla during geomagnetic storms, depending on their strength. It's in many ways driven by this ring current. One thing that happens during a geomagnetic storm is that you get a big enhancement of oxygen ions into the ring current from the ionosphere. So for some reason, oxygen ions from the atmosphere get pushed further out from the Earth, and they have a quite a bit heavier mass than protons, and they carry a charge, so they really start to create these stronger magnetic fields as a result. The ring current gets greatly enhanced. It strengthens, that weakens the horizontal magnetic field even further, but those oxygen ions, they degrade pretty quickly, lasting just a few days at most, and then the ring current will return to normal unless it's continuously fed with new energy from solar wind and flares and things of that nature. So Earth's plasmasphere has a big influence on the magnetic field on our time scale, and it's really the plasmasphere that's allowing for some of these more unusual things like very low latitude aurora to be seen. It's because the plasmasphere is under a lot of changes over the past 150 years through things like power line harmonic resonance, which I'll talk about more. This is something most people aren't aware of, and it explains what's happening to Earth's magnetic field better than, for example, a possible excursion or reversal. But we'll get into that more later on. Let's go even a little bit more in depth on the plasmasphere and the magnetosphere and how they interact together. Now remember that in space, plasma is the dominant form of matter. That's because it's so energetic, aka it's higher vibrational, that it is able to escape the pull of gravity. It has more energy at its disposal to move against the force of gravity. It's higher vibrational than solids, liquids, and gases. So the lower atmosphere is made up of gases, and then as they become more energetic, they need more space and they spread out, and eventually get to the ionosphere at 50 and 100 kilometers up, going all the way to 1,000 kilometers above the surface of the planet, which is a lightly ionized plasma. And then you have like the radiation belts, which are plasma ions. The plasma sheet of the magneto tail is very, very energetic, but not that dense. So in space, plasma is the dominant form of matter, and it decreases in density the further away you get. Now, again, plasma carries a charge, and its movement creates these magnetic fields. So Earth's magnetic field strength drops off quite rapidly via the inverse square law, just like any other magnetic field. And it's where it has the same strength as the interplanetary magnetic field that's where they connect together. So here we have Earth's magnetic field, and you can see the lines in the field emanating out, and eventually it'll reach a strength of about 20 nanotesla, 10 nanotesla, 5 nanotesla, and it's at that zone that it connects with the interplanetary magnetic field. Again, there's only one magnetic field. The Earth is contributing and disturbing that universal magnetic field, just like the sun, just like anything else is to some degree. And so eventually these magnetic fields, depending on their strength, they just kind of go from one to the next. And that's what happens with the Earth. It just kind of blends into the interplanetary magnetic field, which blends into the solar magnetic field. And at different parts of the solar system, it blends into the Jupiterian magnetic field, and so on and so forth. Now, things like coronal mass ejections and solar flares impact the interplanetary magnetic field because effectively they push out a bunch of plasma ions from the sun into interplanetary space. So here the circle is 1 AU, this is Earth's orbit, and there's the sun, and you can see the particle density from a coronal mass ejection, and you see how wide it is. It's quite significant. This is the Parker spiral because the sun is rotating and creates these Parker spirals, and solar ions and wind typically flow along these spiral paths. And you can see that the particle density is higher, closer to the center, but it still is significantly higher than the normal background, even pretty far away. And it can even wrap around in some instances behind the sun. So you have things like solar flares and coronal mass ejections loading interplanetary space with more of these plasma ions. And then when they interact with Earth's magnetic field, they can strengthen the interplanetary magnetic field, and therefore they can connect to Earth's magnetic field at deeper and deeper levels. And that allows for more energy and plasma ions and particles and everything to pierce deeper into the plasmasphere, and therefore have stronger changes to Earth's magnetic field. This varies with the solar cycle. So there is a 11-year solar cycle. The sun flips its magnetic field every 11 years on average. We are going to talk about that more in just a little bit. But what we see here is that about 7 months after solar maximum, there is a sharp increase in the interplanetary magnetic field. This was for solar cycle 24. This may not be indicative of every single solar cycle, but even for solar cycle 24, which is quite weak, we saw a strengthening in the interplanetary magnetic field from about 2.5 to all the way nearly 4.5 nanotesla, and then it decreased from there all the way to solar minimum. So when you have a stronger interplanetary magnetic field, you're going to have bigger magnetic field changes to our planet. Now, this isn't probably affecting the core in any significant way. This is too short of a time scale, but it does affect us as humans on our human time scale. And that's why I wanted to mention this, because this is what a lot of people are getting kind of confused by. They are seeing these changes to the magnetic field and aurora and geomagnetic storms, and things like the KP index and the DST index are having these big changes, and they think it may be due to something like an excursion or a reversal, but in reality, it's from things that we're just now starting to research, understand, like solar cycles and the interplanetary magnetic field and the plasmasphere. And we've only been collecting this data for a few decades now in any qualitative way. So there's a lot that we don't know, a lot that we're still learning. And also, the further back in time you go, the worse our historical records get. So there's also just the fact that a lot of this stuff that's happening to Earth and Earth's magnetic field is just kind of being recorded for the first time and really being seen and observed by a large amount of people. Plasmasphere, magnetosphere interactions are still not understood well, but it is things like that which influence Earth's magnetic field on timescales that we interact with too. To better understand the impact of the interplanetary magnetic field and of space weather on Earth's magnetic field, let's look at a model of the interplanetary magnetic field during a period of ambient conditions. Here we have the sun in yellow, and here we have the Earth in green. And we see the plasma density there for the top and the radial velocity of this solar wind at the bottom. So you'll see this co-rotating interaction region there of higher plasma density is followed by faster velocity plasma ions. And when these co-rotating interaction regions impact the Earth, they will squeeze on Earth's magnetic field and they will change the ion populations of the radiation belts and their energy, and they'll shift the entire plasmasphere around quite a bit. And that's what changes the magnetic field's shape and its size and its strength on the timescales that we see for geomagnetic storms. So we see that the sun is always releasing this solar wind, and it often forms these big co-rotating interaction regions, these sears. Other times it's more diffuse and spread out, and it's really a combination of density and velocity that is what matters in regards to the impact of the interplanetary magnetic field. But because there is plasma density across the entire space that's surrounding the sun and the Earth and even further out, this all carries a magnetic field to it. You'll see here that there is variations in the density going up, down, and then sometimes there'll be even a higher rise. And this is an ambient model, so it's not showing like a solar flare impact or coronal mass ejection. I just wanted to show what this does under normal situations. And anytime something like a co-rotating interaction region passes by the Earth, that's going to change Earth's magnetic field, because it's going to press on it more, and it's also going to inject more solar plasma ions into the plasmasphere, and that will reorganize and change the dynamics of the plasmasphere, which also changes the magnetic field. But this is all occurring on time scales of hours to days, and rarely on the weekly time scale. So what is power line harmonic resonance? I've been hinting at this throughout this video. This is something that has been studied before. It was first observed back in the 70s and the 80s, and it's only amplified since then. But there really isn't much attention brought to this because it's a little bit of a, I don't want to call it a political issue, but it's something that a lot of people don't want to bring their attention to. So let's remember that Ørsted's law is that an electric current creates a magnetic field around it. What happens during geomagnetic storms is that you get these ion precipitation events. Is that you have ions from the radiation belts precipitate down into the ionosphere and into the atmosphere, and that changes weather dynamics and increases various energies like the Schumann resonances and more. So what we do see during geomagnetic storms and these strong ion precipitation events is that Earth's magnetic field is weakened. Now, one of the things that we know of is a phenomenon called ion cyclotron resonance. And these plasma ions, they have certain frequencies that they resonate at, and they are in the extremely low frequency band. So this is 30 hertz, this is 5 hertz, this is 50 hertz, 60 hertz. It depends on what the ion is. It's an electron, a proton, oxygen ion, what have you. But what we've done by electrifying the planet, we have power grids all across North America, power grids all across Europe, Asia, is that we have created these extremely powerful magnetic fields that propagate outwards all the way into the ionosphere and into the plasmasphere at the same frequencies of these ions, at these ion cyclotron resonance frequencies. So they first observed power line harmonic resonance in the late 70s and 80s, and they showed this is where the maxima occurred, which is, as you can see, is over these populated areas, specifically North America and then Europe here. And we can understand power line harmonic resonance better by reading some quotes from The Body Electric by Robert Becker and Gary Selden. This is from 1985, and there has been more recent research that just came out in the past few years. All the research papers are linked in the video description, by the way. So around 1900, Nikola Tesla theorized that extremely low frequency and very low frequency radiation could enter into the magnetosphere and change its structure. He has recently been proven right. The magnetosphere and its Van Allen belts, the radiation belts of trapped particles, produce many kinds of electromagnetic radiation. Many of them result from very low frequency waves produced by lightning, which bounce back and forth from pole to pole along magnetic ducts in the magnetosphere. This resonance amplifies the original very low frequency waves enormously. Here is what we're talking about. This is the electron L slot. Lightning creates spherics, and those very low frequency waves will travel along these magnetic field lines, and through wave particle interactions, they can cause the ions that are here to dislodge from their normal resonance and then precipitate down into the ionosphere. Now remember, the movement of ions is what creates magnetic fields, and this can decrease the strength of magnetic fields. Now a thunderstorm is just a transient event. You have a thunderstorm, it creates a little bit of spherics, and maybe there's space weather that's causing some of this to occur, and you get a temporary reduction in Earth's magnetic field strength. But the thing with our power grids is that we have them turned on 24/7, and they have been increasing in strength as more and more people come online and we need more and more energy. So the stronger these power grids become, the stronger the magnetic fields that they produce at these resonant frequencies, at these ion gyrotron resonant frequencies, and the more and more they're pulling ions from the radiation belts and the ring current down into the ionosphere and the atmosphere. So they may even be responsible for the South Atlantic anomaly, because if you notice here, these magnetic field lines travel from the northern hemisphere to the southern hemisphere, and we have most of the Earth's landmass is in the northern hemisphere, specifically eastern seaboard, and North America is the highest energy density because of the USA. And it is no surprise that the South Atlantic anomaly is located over this part of the planet, which is where that resonant field line travels to. So let's get back to this. Artificial energies from power lines are similarly amplified high above the Earth, a phenomenon known as power line harmonic resonance. So you have these power lines, these energy fields created from the power grid. They are strengthened as a result of being trapped in these magnetic ducts, just like spherics and other types of natural electromagnetic energies. Radio and microwave energy also resonates in the magnetosphere. This amplified energy interacts with the particles in the Van Allen belts, producing a fallout of charged particles that serve as nuclei for raindrops. And in 1983, measurements from the Ariel 3 and 4 weather satellites showed that the enormous amount of power line harmonic resonance over North America had created a permanent duct from the magnetosphere down into the upper atmosphere, resulting in a continuous release of ions and energy over the whole continent. So we can go back really quick. It's right here. And look at how the magnetic field has changed over North America from January to June of 2014. And that would be right where that magnetic duct is. So there's quite a lot of evidence supporting power line harmonic resonance and how it's been interacting with Earth's magnetic field in a big way. Thunderstorms have been 25% more frequent over North America between 1930 and 1975 than they had been from 1900 to 1930. That could be a correlation, that may be causation. It now seems feasible that it's possible to induce catastrophic climate change over a target country, and even without such weather warfare, continued expansion of the electrical power system threatens the viability of all life on Earth. I believe the ultimate weapon is manipulation of our electromagnetic environment because it is imperceptibly subtle and strikes at the core of life itself. This is from The Body Electric by Robert Becker and Gary Selden, a highly informative book on how electromagnetic energies interact with biology and how these energies exist on the planet. So just wanted to highlight that. A lot more research needs to be done on power line harmonic resonance, but it definitely is a factor that is interacting with the plasmasphere and changing Earth's magnetic field. So I was obligated to mention it because as you get these ions moving and precipitating downwards, that's going to change Earth's magnetic field, and it is a transient event. If we flipped off all the power grids tomorrow and left them off, then within just a few weeks, I'd imagine, Earth's magnetic field and the plasmasphere would return to normal. But we've been measuring Earth's magnetic field within this environment the whole time. Our best and most recent magnetometers, which were developed in the 20s and 30s and 50s, they of course existed when we already had strong power grids. So even like the first measurements of the radiation belts, which were done when we sent out probes in the 50s and the 60s into space, they were already measuring the radiation belts under the influence of these power grids, under the influence of an electrified planet. So we don't know what the radiation belts looked like before we already were tampering them with things like power line harmonic resonance. So we're playing with energetic systems that we don't fully understand through the electrification of our planet. And that could be one of the reasons why Earth's magnetic field is changing in certain ways that are hard to explain. Right now, geoscientists are looking at things like wave oscillations at the core mantle boundary, and that certainly may be a causative or contributing factor. But it is also likely that things like power line harmonic resonance are a big influence that we are not addressing because it's something that people don't really necessarily want to address, because it begs us to ask the question of what will we do if we turn off our power grids and change our modern way of life. But I wanted to be comprehensive in this video and discuss all the things that are interacting with Earth's magnetic field, and power line harmonic resonance is one of those things. So whether you take Robert Becker and what he says seriously or not, I recommend you read his book. It's full of fascinating information on biologic regeneration and the experiments that he did, helping people healing with their bones and everything. And then he went into the more of the geophysics at play. One very notable way that the sun and the interplanetary magnetic field and space weather and solar flares and everything interacts and changes Earth's magnetic field is through the creation of geomagnetic pulsations, which are near 0 Hertz waves that exist in Earth's magnetic field. There's different classes of pulsations. We have PC1 pulsations that have a time period of 0.2 to 5 seconds. This gives them a frequency of 0.2 to 5 Hertz. And then you have very, very, very low frequency pulsations like PC5 pulsations that have a time period of 150 to 600 seconds. So this is a very, very long wavelength close to 0 Hertz. The first time geomagnetic pulsations were observed was during the now infamous 1859 Carrington event, when a massive coronal mass ejection impacted the Earth. And the stronger the geomagnetic storm, the stronger geomagnetic pulsations may be. For example, one geomagnetic storm that had a magnitude of negative 80 nanotesla on the DST geomagnetic disturbance index produced PC3 pulsations with a strength of 0.5 to 1 nanotesla, and then PC4 pulsations were generated 1 to 1.5 nanotesla in strength, and PC5 pulsations, which have the lowest frequency, were generated with a strength of over 2 nanotesla. So this is not terribly significant in relation to the Earth's overall magnetic field strength, but this is an example of how a geomagnetic storm that is moderate in strength, negative 80 nanotesla on the DST index, can generate these pulsations and what their strengths may be. These geomagnetic pulsations are also known as field line resonances. This is graphically depicted here with this undulation in this colored field line. And the lower the frequency and the longer the wavelength of an electromagnetic wave, the deeper it can penetrate into various things. So these geomagnetic pulsations interact with the Earth, of course, in near-Earth space and in the plasmasphere. That's where they're generated. They can also be created at the magnetopause, where solar wind is hitting Earth's magnetic field. They can be created in the magnetotail. And then they can travel all the way through the ionosphere and the atmosphere and through the surface down into the crust and perhaps even the mantle if they are of a low enough frequency. So The magnetic field has a static and it also has time-varying components. Our static magnetic field, 30,000 nanotesla in strength near the equator, and 60,000 or so nanotesla in strength at the poles. But then these pulsations are kind of rippling through that static field. Direct electrical currents are what create that stable magnetic field, and it's alternating electric currents that create pulsed magnetic fields. So Earth's magnetic field, as I just touched on, is made up of both. One very notable type of geomagnetic pulsation that is just slightly higher frequency than PC1 pulsations would be Schumann resonances. These are pulsations in the 7 to 45 hertz range. They interact with us biologically. Just a quick note is that strong geomagnetic changes can even trigger stress responses and cause heart problems in sensitive individuals. Here you can see a big change in, let's say, the magnetic field strength. This is just representative, and you'll see that there can be a lag time with heart rate variability, and that can trigger things like arrhythmias, and it's been shown that during geomagnetic storms, there's a higher rate of heart attacks and other phenomenon like that. So these geomagnetic pulsations are one of the aspects of Earth's magnetic field that interact with us the most biologically. And the lower the frequency of these pulsations, the longer the wavelength, and the more that they can get into all the different energy systems of the planet. Because the higher frequency waves will attenuate out, they'll be absorbed, but the lower frequency waves are the ones that really have these big impacts over time, both on different geophysical systems, like in the lithosphere, and also for the biosphere. For us, it's these very low frequency pulsations that interact with our heart and synchronize our heart very, very strongly. Now, these types of pulsations are always happening, especially during geomagnetic storms. We can look at some data here, and you see this is 8 hertz, this is 0 hertz. So if there's 4 hertz, PC1 pulsation is sub 5 hertz. So anything that is below 5 hertz here would be one of these geomagnetic pulsations. And you can see a lot of activity happening in this sub 5 hertz zone here. This is a spectrogram. You also see the Schumann resonances. These are those standing waves that are higher frequency pulsations, 8 hertz or so and 14 hertz and beyond. This is a really nice zone of pulsations there that occurred during a period of greater geomagnetic volatility. There was an increase in the KP indices during this period of time, but I didn't put it in this slide. But these geomagnetic pulsations are the highest frequency component and change to Earth's magnetic field that we've identified so far. And they occur pretty rapidly, and they are one of the hallmarks of a geomagnetic substorm or storm. And they are one of the aspects of the geomagnetic field that interact with us the most biologically. Let's zoom out a little further in time and look at the Russell-McPherron effect. And from this point forward, we're going to zoom out progressively further and further, eventually looking at geomagnetic jerks and excursions and reversals. But the Russell-McPherron effect is very important to know. This is a semi-annual variation of geomagnetic activity that occurs every equinox. So we have the spring equinox, which is in March, and then we have the fall equinox, which is in September. And the Russell-McPherron effect is effectively Earth's magnetic field couples to the interplanetary magnetic field differently depending on what time of year it is, because this is based on Earth's rotation. So you see here the magnetic field can be perturbed more strongly during the equinoxes because solar plasma energy can be injected into the plasmasphere very easily because it connects very easily to the interplanetary magnetic field during this Russell-McPherron effect. So during, let's say, like a solar maximum, a strong time period, we see the Russell-McPherron effect is very strong, and then during a quiet solar period, it still exists, but it's more diminished. Now, this happens because Earth has a rotational axis, it's tilted, and then the magnetic field, the dipole, is also tilted 10 degrees from that rotational axis. So when the Earth is rotating around the sun, depending on where it is, it will have its magnetic field aligned differently to the sun. And it's during the autumn and the spring that Earth's magnetic field is in this conducive position to connect very readily to the interplanetary magnetic field. What happens during this time is that space weather will trigger stronger geomagnetic storms than it would have otherwise. For example, during the winter or the summer solstice. So during the equinoctial months, the Earth is more effective at extracting energy from space weather. 40% more energy is injected into Earth's magnetosphere during the months of, let's say, like March and April and September, October, which results in 2 times more geomagnetic storms during the equinoxes than the solstices. And this effect peaks slightly after each equinox. We can see that here, especially for the strong and the medium. We see it is strongest in October for the fall and then in April. And electron fluxes are 3 to 12 times higher during the equinoxes than during the solstices. So this is an important aspect because electrons are one of the primary plasma ions that exist within our plasmasphere, within the interplanetary magnetic field, within the ring current. And so the Russell-McPherron effect is a semi-annual variation of geomagnetic activity. It's important to know because it's influencing whether there will be a geomagnetic storm or not in the first place, and if there is, how strong it is. You could have a big increase in magnetic field strength for the interplanetary magnetic field, but if it's during the solstice, a lot of that will just kind of skirt around the Earth because it's not going to couple easily with Earth's magnetic field. Whereas if that same solar flare or high-speed stream from a coronal hole was emitted during, let's say, the equinox, then you're going to have a stronger geomagnetic storm result. At least it's going to be much, much more likely. So these are changes to Earth's magnetic field that occur every 6 months that influence all these energetic factors that exist within the plasmasphere and in the ionosphere and in the Schumann resonances and the atmosphere. And it's important to know because these are changes to Earth's magnetic field, just not on the longer time durations that most people think of, which would be like jerks and excursions and reversals. So let's talk about geomagnetic jerks. These are very interesting, and there may be one that is occurring next year in 2024, so it's very relevant to this time period right now. Geomagnetic jerks are small-scale variations in Earth's magnetic field that occur every few years. Now, since the year 2000, we have observed geomagnetic jerks in 2003, 2007, 2011, 2014, 2017, and 2020. So that is about a 3 to 4 year time cycle. And so it's likely that we will see a geomagnetic jerk in 2024. And this can be visualized very nicely here with this graphic. This is a magnetic pulse from the core mantle boundary that has a maximum and a minimum, and each one corresponds with a geomagnetic jerk. So here we have a big pulse, and then it reaches this low, and then there's a new pulse, and then it reaches a low, and it kind of goes through this oscillation. So geomagnetic jerks are a result of core mantle boundary long period standing wave oscillations. These are just effectively very, very long time period resonances that occur deep within the Earth, and it changes the magnetic field by about at the maximum 15 nanotesla on the negative or on the positive. The most commonly seen change is about 5 nanotesla. We can look here and we can see these changes on the Earth there. And here in dark red, it's 15 nanotesla, and dark blue, it's negative 15 nanotesla. And we see that typically it's more in these softer colors. And you see how these geomagnetic jerks, they change the magnetic field in different places, and they go in this rhythmic cycle. So where it is on the positive here, now it is in the negative there. On top is the 2017 jerk, and down below is the 2020 jerk. So they kind of go through this up and down cycle, and one place may see an increase, and then 4 years later you'll see a decrease in magnetic field strength as a result. And we've been able to identify these geomagnetic jerks more readily in the past 20 years or so because satellites can effectively measure the geomagnetic field hundreds of kilometers below Earth's surface by observing extremely low frequency signals over time. So it's easier to see these up in space than at the surface because there's a lot of magnetic interference at the surface, And in space, the overall changes of Earth's magnetic field sometimes are less drastic. And so with the satellite constellations that we put up, we've been able to start elucidating some of these trends from the deep interior of our planet. We're seeing things like these standing wave oscillations, which is basically like a very, very low frequency pulse that is occurring at the core mantle boundary and even deeper. So very interesting to think about. And they are also similar in the fact that they go through a similar time range as solar cycles. And what I want to mention is that this next geomagnetic jerk that's likely to occur in 2024 is going to correlate and happen at the same time as solar cycle 25 maximum, which is probably going to start around 2024 and go through 2026, reaching its peak, we expect, in about 2025. So we are going to have this geomagnetic jerk that is changing the magnetic field, not in a big way. Again, this is just 15 nanotesla on each side, but it is going to be altering Earth's magnetic field on that time scale during solar cycle 25 maximum. And we're going to talk more about solar cycles in just a little bit. One of the most notable changes that has occurred to Earth's magnetic field in recent time has been the movement of the magnetic North Pole from Canada towards Siberia. Now, the magnetic North Pole has been drifting from the Canadian Arctic towards Siberia since the first in situ measurements were taken in 1831. But what's notable is that this drift began to accelerate in 1990, is now moving as fast as 50 to 60 kilometers per year. What's important to know is that the location of the North Magnetic Pole is largely determined by the size and the strength of these flux lobes here. We have one over Canada and one over Siberia, and you can see how they've changed. In 1999, they were about equivalent in size and strength, and then in 2019, the Canadian flux lobe was much smaller, and the Siberian flux lobe has strengthened quite a bit. So it's believed that an alteration in the pattern of core flow starting in 1970 began to alter these flux lobes, causing the magnetic North Pole to move from Canada to Siberia along what's known as a magnetic trough. Now, what are these flux lobes? If we zoom out, we can look at Earth's magnetic field. Here we have the interplanetary magnetic field represented by this line. Here we have Earth's magnetic field. There is solar wind. And we see these polar cusps, these funnels in Earth's magnetic field that will take these plasma ions and bring them in towards the poles, causing aurora borealis and australis, depending on which hemisphere you're in. So these flux lobes are features of those larger polar cusps. The magnetic field in general at the poles will funnel out like we see here. But then for the northern hemisphere, it has these flux lobes that are smaller features within those larger ones. And at times, there's even been a 3 flux lobe structure that has developed in the northern hemisphere. And this is likely dependent on what's happening within the mantle and within the core. So between 1990 and 2019, the Siberian patch intensified from negative 60,500 nanotesla to negative 60,600 nanotesla, while Canada decreased from negative 59,600 nanotesla to negative 58,000 nanotesla. And what we'll see here is that the magnetic North Pole has removed in a remarkably linear fashion, which is pretty unprecedented in recent historical records. And that's because it's following a pretty clear magnetic trough of low horizontal field strength. Now remember that the magnetic poles as measured at the surface are only an indirect indicator of the state of Earth's geodynamo and the generation of Earth's magnetic field at the core and what's happening in the mantle. And we actually have analogs of acceleration that are similar to what's happening today that occurred at 45,000 BCE, so 65,000 years ago, and also at 1300 BCE, where the speed reached about 3 to 4 times the average today. So we can and have seen the magnetic poles move pretty rapidly depending on these changes to the core and the mantle. And it's likely that these changes that happen are occurring as a result of geologic factors such as subduction. Now, a question to ask is, why are there these flux lobes in the northern hemisphere but not in the southern hemisphere? The south magnetic pole has not been drifting in any real significant way, but the north one has. And at times, we have a three-patch structure developed. So what's creating all this radical change in the magnetic field in the northern hemisphere? Well, as you can actually just see from this graphic, most of the world's landmass is concentrated in the northern hemisphere. And as a result, you're going to get most of the subduction zones in the northern hemisphere. Of course, you have the subduction zone for South America, but for the most part, the largest subduction zones, and the majority of them, are located in the northern hemisphere. So subduction zones, as we talked about earlier, can carry these magnetite zones. And as they are going and moving through the Earth and traveling downwards into the mantle, they can change the magnetic field structure. Now, that's not happening on the human time scale, but over longer periods of time, this could create kind of these uneven magnetic field arrangements that we're seeing here. And if you do have a part of a subduction slab that eventually reaches a depth and it can become part of the mantle, and that remnant magnetization disappears, then all of a sudden you can have a liberation of the magnetic field in that zone, and that could change the magnetic field dynamics like we see. So if we go to the North Magnetic Pole location and zoom in, we'll see how it's changed from 1590 to the most recent measurement in 2007. And I want to be very clear with something here, which is that the last direct measurement that we have of the North Magnetic Pole was taken in 2007, and everything else has been postulated from indirect observations and from modeling. That's very important. But let's look here. Here's how the North Magnetic Pole has moved from 1590 onwards. Here we have 1904. You see that it has moved, but the rate of change wasn't that great. And then what we see here, these are the observed pole locations. The yellow squares are where they actually got real measurements of the magnetic pole. They found where a compass dip needle pointed exactly vertical. So you see, these are our best data points. And the last one, you see 1994, then there's this acceleration. They found it again in 2001, had moved quite a bit, and then this acceleration in 2007. And since then, everything else has been based on models. So you have to take this with a grain of salt, because if you're not actually measuring where the magnetic North Pole is, pointing exactly vertically down towards Earth's surface, then it's kind of a ambiguous measurement. It's based on a observation station that's over here combined with data from this one, and one that's 5,000 kilometers away and from satellites. But satellites aren't at Earth's surface, so this is all very indirect. So we do not have a exact in situ North Magnetic Pole location for this decade. We haven't collected one since 2007, as best as I know. Maybe the Russians have collected one because it's closer to them now, but I haven't found that research. And I think that most geoscientists have become content with modeling the location of the magnetic pole rather than getting in situ measurements, because it's difficult. If you are on the ocean and the boat is rocking and it's swaying, and it's also highly dependent on ionospheric currents and geomagnetic storms and things of this nature, it's difficult to get these measurements, especially when it's not over land. So we don't have the exact North Magnetic Pole location, and everything has just been estimated. So anyone that's telling you exactly where it is not giving you all the information, because no one right now knows exactly where it is unless they were to go out there with a dip compass and they were to find it. And that measurement has not been taken since 2007. Regardless, this magnetic pole is moving quickly because it's moving from that Canadian flux lobe to the Siberian flux lobe. And this right here is a trough of low magnetic field intensity in the horizontal component. So it's able to rapidly move from one to the other. What is interesting is that this has occurred really rapidly since 19 1994 or so. And there's been a lot of technological advancement since then, and things like power line harmonic resonance may be contributing to this movement of the North Magnetic Pole. Let's look at some more changes that have occurred to Earth's magnetic field over recent time periods. Here we have from 8,000 years ago to the modern day, and we see Earth's magnetic field strength has decreased from about 3,000 to 2,000 years ago. During the period of the Greeks, it was high in the Balkans at a strength of about 70,000 nanotesla, as measured by archaeo-intensity data collected from pottery sherds, and it has decreased since then. But what you'll see is that if you go back in time to about the Neolithic, which was 5,000, 6,000, 7,000 plus years ago, the magnetic field intensity for the Balkan region was about the same as it is today. We can look more specifically at this time scale here from 3,000 years ago to the modern day, and we'll see that spike there in the intensity and also here. But we'll see that we have a lot more data points for the more recent time period. That of course makes sense. We're going to have better resolution the closer to the present we get. And we see that the magnetic field is starting to kind of stabilize in its strength. It's not decreasing so rapidly. And again, back here, this was normal. It reached this kind of normal zone. So this could have been an increase, and perhaps it just stabilizes out. It's hard to say. We don't know what Earth's magnetic field is going to do in the future. This is about 8,000 years that we're looking at here. And then this time scale here is about 3,000 years. And you see that there are these intensity variations that occur. So this is not at all abnormal. And one of the things to remember is that this is our most recent 3,000 years of data. We don't have multiple, quote unquote, most recent 3,000 years of data. It only gets fuzzier and lower resolution the further back we go. So it's not like we have multiple of these data sets to compare to. And if we do, let's say, look at a similar 3,000 time year range from, let's say, like 50,000 years ago, that 50,000 year ago data set is inherently going to be lower resolution, have greater error than our most recent 3,000 years or our most recent 10,000 years of data. So we have to take what we see in the geologic record with a little bit of a grain of salt, because a lot of it is based on assumptions or age uncertainties and things of that nature. So there's a lot at play. And if we look at our past 10,000 years, we see a relatively normal looking variation in magnetic field strength. It was about what it is now. Back in the Neolithic, there was a strengthening during like the Bronze Age and the Iron Age, and it's gone back to these Neolithic values, at least for the Balkan region. Okay, geomagnetic excursions, let's get into it. This may have been what you're waiting for. These are very, very interesting changes to Earth's magnetic field. The first evidence of a geomagnetic excursion was observed in 1904 and 1906 from magnetization directions that were recorded from baked sedimentary rocks. And so we've had some knowledge about changes to Earth's magnetic field that are larger than just some of these things like geomagnetic pulsations for a while. Eventually we learned about reversals as well. But excursions occur more frequently than reversals. Reversals are the least frequent changes that occur to Earth's magnetic field. And the most recent geomagnetic excursions that we have really good, confident data on are the Mono Lake Auckland excursion that occurred about 30,000 years ago, the Laschamp excursion from about 41 to 42,000 years ago, and then the Norwegian Greenland Sea excursion from 64,000 years ago. And these graphs that we're looking at here, this is the global magnetic field at the beginning of each excursion, and it's approximated, of course, in microtesla. And you can see here that they're quite a bit weaker. For example, the Laschamp excursion, which was a very notable, very strong excursion, it may have even been an aborted reversal. You see that the magnetic field is quite a bit weaker than it is in the modern day. Now, Mono Lake had a stronger magnetic field at the beginning, but it was also a weaker excursion. And then the Norwegian Greenland Sea also had a fairly weak magnetic field, as we can see, but it did have a strong North Pole magnetic field there. Now, these are created from models. We can look at some data here. This is for the past 770,000 years, and this shows the excursions. And this is 4 different studies. So the first one, second, third study, and then the fourth one is for the research paper that I read, where they really looked at just the best available data that had really good controls on it. And this has the Blake excursion at 120,000 years ago, the Laschamp excursion, and the Mono Lake. And some of these studies have them dated slightly differently. People originally thought the Laschamp excursion happened at the same time the Mono Lake excursion happened. They didn't know the Mono Lake excursion at the time. So there is a lot of uncertainty with these in general, and there's a lot of issues in regards to them because you have to account for a lot of different variables, which makes it difficult to tease out exactly what happened. And this, I'm sorry that this is so low resolution, but this is showing what has been very well confirmed, what has strong evidence for occurring, and what has some evidence. So you can see that the Iceland Basin excursion 188,000 years ago, well confirmed, strong excursion. Blake excursion, well confirmed. Laschamp, well confirmed. Mono Lake at 32,000 years ago. Norwegian Greenland Sea, they have strong evidence, but not as strong as like Laschamp and Blake. And then there's things like the Gothenburg excursion 13,000 years ago. Maybe it didn't even happen. There's some evidence, but it's not well confirmed. And it's important to talk about that because the fact that the Laschamp excursion and the Blake excursion and Iceland Basin excursion are so well confirmed at time horizons that are further out shows that those were strong excursions. 13,000 years ago, if you don't have good evidence for that excursion, then it probably didn't happen because the time records are much better the closer you get to the present moment. The data becomes higher resolution the closer you get to the present moment. So either these are weaker variations in Earth's magnetic field, or they just haven't been conclusively disproven yet by taking more data points. There may be some data points that support them, but if they haven't been picked up in a very comprehensive way, then they were either weaker or they didn't happen in any significant fashion. So the Laschamp excursion was a very significant excursion. We're going to talk about that more in depth. Here we can look at the distribution of evidence for recent geomagnetic excursions. You can see that for Laschamp, it is just absolutely stacked. There are data points all over the world. And you can see here also how much evidence exists for this time period. Whereas for the recent time period here, yeah, we get some little spikes, and there's the Norwegian Greenland Sea, post-Blake, but the Laschamp dominates the record. So we have an excursion event that has some evidence for 14,000 to 26,000 years ago. Mono Lake has a bit more. Norwegian Greenland Sea has some. Post-Blake has some, but it's really Laschamp that stands out. We can look specifically at what happened during the Laschamp excursion with these virtual geomagnetic poles. And so this is recreated based on the magnetic intensity data and the vector directions that they have. And you can see that the Laschamp excursion had this clockwise movement to it. And so you can see that very clearly. These are different models, but they all generally follow this clockwise direction. And there's other excursions that have been found to have counterclockwise directions. But in general, what happens during an excursion is the geomagnetic pole will go through these mid-latitudes past the equator, go down, and before it fully flips, it will then revert back to its normal polarity. And during past excursions, the magnetic field has fallen below 30,000 nanotesla across wide swaths of the Earth. So this is like the magnetic field strength that we see at the equator right now, but this is basically a magnetic field strength that will exist or even be lower at the poles. So that's why the magnetosphere is so much smaller and weaker, is because the magnetic field strength just goes down so much. So if we look specifically here, this is a really good graphic showing today's magnetosphere. It's about 10 to 15 Earth radius in size. This is, of course, facing the sun. We do have the magneto tail. And then it's showing what happens with Earth's magnetic field during different space weather events during the Laschamp excursion, because the magnetic field strength was depleted. It was 28% of modern levels. And we see that the magnetosphere only went out to about 5 Earth radii. This resulted in a depleted ozone layer, and ultraviolet flux was higher, especially with the equator. And there was aurora down to 40 degrees latitude. The stratosphere was lower, the troposphere was lower, increased ionization, and this is during an active sun. Now, during an inactive sun, the magnetosphere was still 5 Earth radii, but there was in general less of these effects. This is like during a grand solar minimum. So there would have been less of these strong space weather effects during a grand solar minimum, but still during the Laschamp excursion, the magnetosphere was quite weak and it was quite a bit smaller in size. Still, you could have aurora down to about 40 degrees in latitude. And then during something like a solar energetic particle event, where you have a lot of solar protons streaming into the Earth, the magnetosphere would weaken even further, becoming just about 3 Earth radii in overall shape and size on the sunward side. This would cause a big increase in ultraviolet radiation, a big drop in ozone, and perhaps even global aurora, definitely super visible during the night, and big increases in atmospheric ionization, major impacts at low latitudes. And so during geomagnetic excursions, during that time period where the magnetic field is very weak, and the magnetic field is also much smaller, these space weather impacts and these geomagnetic storms are much stronger, and this influences the atmosphere. This influences how much ozone is produced, and ultraviolet radiation therefore influences the climate and creates a biologic pressure. So these excursions are linked to extinction events. Whether these are minor extinction events or major extinction events, they may have been one of the factors that put pressure on the demise of the Neanderthals, because that lines up with the Laschamp excursion. They can last anywhere from about 500 to 3,000 years long. They have regional durations that are different than the global duration. Like, for example, the magnetic field strength may revert back to normal faster in one part of the planet than the other. 2 different models for the Laschamp excursion show the global duration being 400 years and the other one being 1,800 years long. So quite a bit of variation there. But in general, it's in that 500 to 2,000 year time zone. And again, I just want to highlight that in general, fields like archaeology and geology, the further back you go in time, the lower the resolution becomes. So the fact that the Laschamp excursion at 41,000 years ago has the most supporting evidence means that it was a very big event, and that more recent proposed excursions were weaker. Because if they were stronger, they would stick out like a sore thumb. They would be much stronger and they would have been found sooner than the Laschamp excursion. So that is our most recent, well-documented, strong excursion. Mono Lake also has very good evidence for it. And then we have the Norwegian Greenland Sea at 64,000 years ago. Again, there are others that have strong evidence, but those are the big ones. And those are the most important ones for us to focus in on as to what actually happens during a geomagnetic excursion. Geomagnetic excursions are transient events where Earth's dipole magnetic field weakens and the poles begin to wander. They are not full pole reversals. One of the theories of geomagnetic excursions is that a full pole reversal takes some time. And so with an excursion, the liquid outer core will reverse polarity, but the change does not persist long enough to diffuse into the inner core and reverse the polarity there. And it's estimated that diffusion of that magnetic field from the outer core to the inner core takes about 3,000 years. And therefore, an excursion, if it can't flip that inner core, it will then revert back to the normal polarity. And most excursions that have been measured have durations of less than 3,000 years. Now, there's also evidence that suggests that the path that excursions take is controlled by core mantle boundary structures. And there's three main theories that exist surrounding why excursions happen. The first one is that there is a significant rotation of the dipole axis away from Earth's rotational axis, accompanied by a decrease in non-dipole power. If we go back to the beginning, you remember that I talked about how Earth's magnetic field is made up of a dipole, and then there's these higher order dipoles, and then there's also just in general non-dipole magnetic field strength. So if the dipole is actually moving away from the rotation axis and the non-dipole power goes down, then that would explain the intensity lows that we see, the magnetic field strength decreases that we see during excursion, and also why the magnetic poles are moving direction and changing quite dramatically during excursions. The second main theory is that there is a decrease of the main dipole field such that the non-dipole field becomes dominant. And as a result, because the non-dipole field is quite weak, the magnetic field strength is decreased and there's no dominant dipole direction. So we see them drift to these southern latitudes and the equator and everything. And then the third main theory is that there are localized perturbations in Earth's outer core that cause regional excursions with a strong non-dipole field, but there's no complete reversal. And there's also evidence that excursions may occur when the dipole field transfers some of its strength to the non-dipole field. So there's a lot of unknowns about geomagnetic excursions, but like for example, the Laschamp, it is well documented. So we know they happen and we're kind of piecing our way as to how they occur back from that data. And this is collected from like lava flows and magnetic sands and how they're deposited and their orientational directions. And it's a lot of field work and collecting this. And some of the ambiguities are in like, was the data collected accurately? Are these magnetic orientation vectors accurate? Is the dating accurate? Now, some of the challenges in modeling paleomagnetic data like we see here is that there's limited data coverage. I mean, we see that really well here. There's just limited data coverage for some of these excursions compared to the Laschamp excursion. And that there's a lack of full vector data, like exactly in which direction are these magnetization directions pointing. And the data uncertainties can exist in terms of the age and also the paleomagnetic values. And there's also variable resolution across these time series. So you could look at, for example, this data set here could have a time resolution or a magnetic resolution that differs from this one, that differs from this one. And that makes it all hard to piece together. And that's very, very important to know, because before you're going to come to any conclusion on whether an excursion happened, there has to be an overwhelming amount of evidence that supports it. So the Laschamp excursion was the first reported geomagnetic excursion. To this day, it's still the most well-established excursion. And yeah, it traced this clockwise loop and then stabilized. And it was about 1,500 years long. Geomagnetic reversals. This is the big brother of geomagnetic excursions. This is what happens very, very rarely on our planet, though there have been variations within the geologic record of how often geomagnetic reversals occur. This is when Earth's magnetic field completely flips. Now, the best cousin that we have to this is that the sun undergoes a magnetic flip every 11 years. This is known as the solar cycle. For the Earth, this does not happen all that often. The last one was 780,000 years ago, approximately. Here we see a simulation of the electromagnetic dynamo of the Earth before, during, and after a pole reversal. So here you see the poles are well located and they're stable, and yeah, there's some chaos and craziness in between, but overall it's a pretty stable structure. But then with the simulation, you see that the magnetic field just goes all types of crazy during the reversal, and then it reorganizes into a new magnetic field with different polarity. It's swapped at the end of the reversal. We can actually look here at the relative magnetic field intensity. This is stylized. And so here is before the reversal, some changes. Then there's this big decrease in the strength of the magnetic field, and then it rebounds and strengthens after the reversal. And that's the biggest fear that people have with geomagnetic reversals or excursions, is that the magnetic field strength goes down so much, and as a result, space weather and solar flares and coronal mass ejections have bigger impacts on the planet. But it's important to note that stronger geomagnetic storms does not mean that the magnetic field is weakening. The magnetic field weakening will definitely mean stronger geomagnetic storms, but there are other factors that affect the strength of geomagnetic storms. So getting back on track, according to paleomagnetic data, the last magnetic field flip was about 780,000 years ago. We are still in this period of magnetic field stability. And during this time period, the past 780,000 years, there have been excursions and jerks, and of course, geomagnetic storms and pulsations. They're all nestled within this larger change in Earth's magnetic field. And for the past 5 million years, there has been a relatively long period of magnetic stability. But if we look back, we can see that there were even longer stretches of time where the magnetic field was stable. For example, the Cretaceous normal was a 40 million year long stretch of time which had no polarity reversals. This is the Cretaceous normal right there. You can see these geomagnetic reversals occur. Sometimes they're just short affairs, sometimes they're longer, represented by thicker bars. And right now we are in this one right here. So it's been a fairly long reversal. You can see here that we have these punctuation marks where the magnetic field is nice and long, and then it goes through these variations that are more frequent here. But we also have these periods of time where it's pretty lockstep, and it's more common to have these very long periods of magnetic field stability. Of course, the resolution goes down with time, but this is based on seafloor data, which is pretty precise. So we do have some good information on the reversals because these are very long time periods. So we can take a large chunk of rocks and look at them and see what the reversal directions are. The problem with understanding what happens during a reversal, or for that matter, during a excursion, is that they are so fast on the geologic timescale, just taking 1,000 years, 2,000, 5,000 years long, that's hard to capture that resolution during the actual event. We can see the before, we can see the after, because they're those longer time periods, but it's during the actual event that's hard to get good data on. It gets fuzzy, and that's one of the problems with better understanding this stuff. So we can look at the past 100,000 years here, just to kind of go back to the fact that there's been no permanent pole reversals during that time period, but that the Laschamp excursion got very close. And you can see here that the virtual geomagnetic pole latitude went down the lowest during the Laschamp. So there were some other periods here. There was a little pulse that occurred there about 20,000 years ago, this up down right there. But the Laschamp really saw this big spike going downwards in the geomagnetic pole location on the planet. It really reached those low latitudes. And if we look at the magnetic field strength during this same time period, you see that that corresponded with a pretty steep decrease in the magnetic field strength, and the other ones did not see as big of a drop. And we see a little magnetic field pulse right there where it strengthened and then decreased at about 15,000 years ago. And we see, these are different models, by the way, the different colors. We see that the field has actually been quite strong, and it's just now going down a little bit. And compared to recent geologic time periods like 80,000 years ago and 60,000 years ago, that it's actually been weaker than it was now. And it was actually right after the field was the strongest that it went through an excursion. So there is a little bit of a parallel looking at this data, seeing that the field has strengthened and now it's starting to go down, but it's hard to say whether or not we're within a time period like this where it got stronger, but then it was stable for 30,000 years, and then another 15,000 before there was that excursion, or whether we are about to undergo a magnetic field excursion. Now, one last thing I want to address is the solar cycle and the concept of magnetic inertia, because this will help to understand what's happening on our planet. and just in general how magnetic fields move and the waves and the rhythms. We talked about this at the beginning, but there's in general this flow, this ebb and this flow and this rhythm and this periodicity to changes to magnetic fields that exist, whether it's a pulsation or it's a jerk that occurs every 4 years, or it's a diurnal variation that occurs every 24 hours, or it's an excursion or a reversal. So the sun provides a good opportunity for us to look at things like magnetic inertia. Because it undergoes a magnetic pole flip approximately every 11 years, this is known as a solar cycle. And though the sun and the earth are quite different, pole reversals from the sun provide a good opportunity to study the physics of magnetic pole reversals in general on human timescales. They happen very rarely on Earth, so we can get high resolution data from the sun and then apply some of these learnings to what happens on the Earth. Now, there are things like grand solar minimums that occur when the sun's dipole doesn't flip. The Maunder minimum was the last one that occurred from 1645 to 1715. They have a lower frequency cycle of occurrence and was clearly demonstrated with solar cycles and grand solar minimums and grand solar maximums, is that there are these periods of magnetic activity nested within each other. At least the sun has them. And what happens with the solar cycle is that a new reversal begins almost immediately after the last reversal finished. So there's a momentum aspect to these reversals. We can see that very nicely here, looking at this data. And we see 2017, that the poles are fairly fixed in their position. 2018, they look nice. 2019 looks the best. 2020 looks the best as well. But then you get to 2021 and it starts to shift again. The magnetic structure begins to shift and it's starting to go through the next reversal. So it hit this nice dipole structure just for a couple years before it started to flip from the solar minimum and to go on solar cycle 25 to go to solar maximum. So Earth has this magnetic inertia momentum. It's much slower, but that does explain reversals and excursions and why they happen with some regular frequency. And that does give us a little bit of an ability to forecast. We can look at the reoccurrence interval for a excursion or for a reversal and say, okay, is the reoccurrence interval coming up? Just like for an earthquake. When was the last time it happened? How often does it happen? Are we within that time window? Same for geomagnetic jerks, which occur for the past 20 years, at least every 4 years. So this is the sunspot numbers from 1750 to 2020. We see how they go up, and then they go down, then they go up, and they kind of settle, and they go up, and they go down. So there are these rhythms in these cycles that have different time periods. And here we see the solar minimums, solar maximums, where there is no dipole. It is at its most unstable right here. This is what the maps look like. Here we have 2010 and 2013, 2020, 2015, and we can see how there are these big changes to the magnetic field structure, especially during maximum. It's just complete chaos. But then for March 2020, we see this nice, perfect solar dipole represented by this structure there. I want to wrap up and discuss why there's all this talk about a geomagnetic excursion or flip right now. Will a geomagnetic excursion happen in the future? The answer is almost certainly yes. The Earth goes through these magnetic field changes at regular intervals, and so unless something absolutely bonkers happens, like the Earth getting destroyed, it'll go through another geomagnetic excursion at some point. Will there be a future reversal at some point? The answer is also yes, though at a different time frequency. It may happen soon. It may happen a million years from now. We don't know. We don't know when these excursions or reversals are going to happen. What we do have more data and information on is the movement of the North Magnetic Pole and Earth's magnetic field. Now, is Earth's magnetic field weakening? The answer is maybe. We know it's weakening to some degree. It's weakened 10% in the past 170 years. There are magnetic observatories that exist all across the world. If the magnetic field strength had dropped in any particularly dramatic fashion, let's say by 20% in 20 years, this would have been observed by thousands of geoscientists and geophysicists independently worldwide through systems like Intermagnet, people with their own magnetometers. All these navigational equipment that we use has to be calibrated to the pole. So if there had been a huge drop in the magnetic field strength, this would have been noticed. And simply put, the magnetic field strength has not dropped that significantly over the past 50 or 100 years. It is changing all the time, but these could be normal variations. We've only been observing this data for the past 150 years. The first magnetic field strength measurement was taken in like 1831. So it's not like we have excellent data on this for thousands of years. This really is a pretty recent field of scientific investigation. And so we're just now starting to understand how the magnetic field changes on all the different time scales, from pulsations to reversals. And in 50 years, 100 years, we're going to know much more. But there's a lot of things that we think are abnormal, that are happening, that probably actually are fairly normal. And it's just because of things like the internet. It's made it really easy for information to be disseminated to anyone. And the internet has also made it easy for anyone to cherry pick data and to sensationalize it. So, I mean, doomsdayers have always existed, and it's easy for them to say things without backing it up with scientific research and data. All the research papers I used to create this video are linked in the video description, so you can look at them. I'm not going to hide those links like others do. Always do your own research and find the original research that is being presented. And I hope you found this video useful in regards to what Earth's magnetic field is actually doing, in regards to how it's generated and what's happening in the plasmasphere and what happens during space weather and solar flare impacts, and how it's changing across time with things like geomagnetic jerks and excursions and reversals. But probabilistically, the chance of a dramatic change to Earth's magnetic field, like an excursion or reversal, is extremely low. Right now, the biggest thing that's happening is the movement of the magnetic North Pole towards the Siberian flux lobe. Best evidence suggests that it will stabilize its position there. But we have to remember that the last in situ measurement taken of the North Magnetic Pole was in 2007. So while we have a kind of a hazy fix on where it is, a rough fix, a rough understanding of where it actually is based on all the magnetic observatories and the magnetic models that we can create from those different data points, in regards to actually standing on the magnetic North Pole with a dip compass and it's pointing 90 degrees vertical towards the ground, that last data was from 2007. So it is 16 years out of date. And so no one knows the exact location of the magnetic North Pole, and therefore the information on its acceleration is still kind of up in the air until we get a new measurement. Then we'll really be able to see, okay, this is where it is now, and the rate of change and its acceleration, its speed over time. So there's a lot that we don't know, but we do know the magnetic field strength and the strength across its different components, X, Y, and Z, at every single magnetic observatory that exists on the planet. So you can find the one that's closest to you using intermagnet.org, and you can look at the magnetic field strength. You can look at it over time. You can look at it as it changes with a geomagnetic storm. Some places will have bigger changes than others. The closer you are to a magnetic pole, whether north or south, the bigger those changes will be. If you're in the equatorial regions, a geomagnetic storm doesn't really change the magnetic field all that much. But sometimes though, it'll see some weakening effects. If you're in the northern hemisphere near, let's say, the North Magnetic Pole, like in Uppsala in Sweden, you may see a 500 nanotesla swing as a result of a geomagnetic storm. And then there's also, of course, the geomagnetic jerks and pulsations and Schumann resonances and all those things. But again, it's very easy for anyone to cherry pick data and to have a good voice and to sensationalize things on the internet. So do your own research, please, please, please. I hope this video has helped you in you performing your own research, and you can go further into this with all the DOI links that I have. I highly encourage you to look more into power line harmonic resonance. This is something that I'm actively researching. It's fascinating, and it's something that is probably the most troubling aspect of everything that I've gone over here. I'm not worried about an excursion personally or reversal happening in our lifetime. I'm not necessarily worried about the movement of the north magnetic pole, but the power line harmonic resonance and the changes to our near-Earth environment as a result of our power grids and of the electrification of our planet with all this energy, that worries me. So I would suggest that you research into that more, and I hope you found this video useful. Thank you so much for watching this video. I hope you found this master guide on Earth's magnetic field valuable. If you did, please like the video and share with others. I've been your host, Stefan. I make a lot of videos on geophysics and space weather and Schumann resonances, and also how these energetic changes affect us biologically and what you can do to stay healthy and grounded during geomagnetic storms and similar phenomenon. So if this sounds interesting and useful to you, please subscribe to my channel. Thanks so much for watching. I've been your host, Stefan Burns. I hope you learned a tremendous amount, and not only do you understand more about the Earth, but I also hope you feel a greater connection to her as well. Now, if you'd like to continue your education, you can click the box on the left of your screen to learn more about Earth's mysterious magnetic anomalies. And if you'd like to check out the entire video playlist, then you can click the box on the right of your screen. Wishing all of you well, thank you so much, and I'll see you all very soon.